Hello, everyone. My name is Abdullah Gharaibeh. I'm from Google, and I'm the co-chair of SIG Scheduling. Today, I'm going to talk about what we've been up to in SIG Scheduling in the past two releases. So this is the agenda for today's talk. So I'm going to quickly go through a quick introduction of what the scheduler is, and then an assorted list of recent developments and planned features. My plan is to go through this quickly, like maybe 25 minutes, and then leave the rest for questions. So what is the scheduler? So like everything else in Kubernetes, it's just another controller. This controller usually runs on the master. It watches for pods and nodes that are created on etcd. And what it does is basically it assigns pods to nodes. It has nothing to do with the pod lifecycle at all. It doesn't actually create and run the pod on the node. The only thing it does is it creates a sub-resource in the pod object that says pod X should run on node Y. Once this happens, the assumption is that the kubelet that runs on the node that was assigned to the pod should pick up that pod, create the pod, and start it up. At that point, the scheduler is handoff, like has nothing to do with the pod. So as I mentioned, the scheduler watches for pods and nodes. Those pods that are added, the new pods that get updated, they are added into a scheduling queue. And this scheduling queue is sorted by pod priority, so it's basically a priority queue. And the scheduler basically picks one pod at a time, runs it through, so far it's been two phases. The first phase is what we call like filtering phase. So we run the pod through a bunch of filters that decides what are the feasible nodes that the pod can run on. Example filters are, as you would expect, is whether the node has enough resources to run the pod based on the pod resource request. Other filters could be, for example, pod affinity, like required pod affinity. We need only to look at the nodes that has the pods that this pod has affinity with, and so on and so forth. So after this phase, we filter out the nodes that are unfeasible, and we end up with a set of feasible nodes. Those feasible nodes go through what we call a scoring phase. Basically, we have a bunch of scoring functions that rank the feasible nodes, and we pick the highest scoring node. Scoring functions can be, for example, preferred pod affinity rather than like required. So if you decide that I prefer that pod X be run with pod Y, so if the node that has pod Y, the node that would have higher ranking than other nodes. Other priority functions, for example, is one that ranks nodes that has already the image that the pod needs. It has, like, for example, a higher ranking, and so on and so forth. So after we score the nodes, we pick the highest scoring node, and then we just do the binding that I mentioned earlier, and then the cycle goes on and on and on. If for some reason the pod ended up after the scheduling cycle with 0 feasible nodes, we place the pod back in what we call a back-off queue. So basically, like the back-off queue, for each pod, it has a back-off timer. We add it back to the active queue so that we can try to schedule the pod again. So what I just described before, this is what we call a scheduling attempt. And we could attempt to schedule a pod multiple times until it's scheduled. And this goes until infinity. So until the pod is scheduled, it will always be moving between the back-off queue and the active queue. We do have something called unschedulable queue, but I don't want to get into too much detail on that right now. OK, so after this quick introduction, I want to talk about what we have been up to recently. So I have like 5 major developments that I want to talk about. The first one, which I think is the most important one, is the scheduling framework. I believe in past KubeCons, we've talked about our plans to restructure, refactor the core of the scheduler into what we call a scheduling framework. And basically, what we wanted to do is we wanted to turn it into a pluggable component, like the previous talk that was here, Core DNS, or if you know, Envoy as well. We wanted to turn the default scheduler into an engine that executes plugins. And the idea is that we wanted to define a number of extension points that we've identified from our past experiences with the scheduler. And those extension points, you can register callback functions and a collection of callback functions that define a specific behavior. We're going to call it a plugin. And I'm going to give a number of examples about this. But what we've identified is the following extension points. So from the top left, the sort. So if what I'm showing here, this line is a scheduling attempt of a plugin. It goes through these phases while we're trying to schedule a specific pod. The sort extension point is a little bit special in that you can only define a single plugin that defines how we sort the scheduling queue. The default scheduling behavior is that, as I mentioned earlier, we sort it by pod priority. But maybe you don't care about pod priority. You want to schedule based on requests or resource requests or whatever custom sorting behavior that you want. So you can customize that now. The second phase is, again, like if you look at it, there is pre-filter, filter, and post-filter. This is what I talked about earlier. It's the phase where we define the feasible nodes. But we found that we needed another two phases, another two extension points before and after the filter that allows us to run to optimize that behavior. Sometimes features like pod affinity, for example, it runs much faster if we do some sort of pre-calculation. And that's what we would usually do in a pre-filter phase. So in a pre-filter phase, we look at the pod, for example, state or even the cluster state. We summarize it. And then for each node in the filtering phase, we execute the filters using the exact same metadata, let's call it, or pre-calculation that we did in the previous extension point. The post-filter, we felt that we didn't really need the pre-scoring, so we called just post-filter. So you either want to release some resources that you allocated in the filter or pre-filter phase. You can also do some sort of pre-scoring. You can also do some sort of pre-calculations or pre-computations before you go into before we're trying to scoring the nodes. And then there's a phase called normalized scoring. So usually the way that we do things is that we execute those extension points per node. But then there are some scoring functions that you want to normalize. Like after you scored each node, you want to do some sort of a normalization. And this is what this extension point allows you to do. And then there's the reserve, where you actually allocate the resources. You decide that, OK, this node is going to take up these resources from this and that node, from this node, for example. And this is where we're going to update the cache that we have in the scheduler to determine that this pod is going to run on this node. And this ends the first phase. We call it the scheduling cycle. The next phase, we call it the binding cycle, runs in a separate Go routine. So now the scheduler in the main Go routine will pick up another pod, and it will go through the green phase that we have here. And in parallel, the binding phase will run for previous pods that are already been associated with a specific node. In the binding phase, as I mentioned before, we try to bind the pod with a node. The reason we do it in a separate Go routine is because it requires calling into the API server, because we want to write and update the pod object with whichever node the pod will run on. And because, as you might know, we do throttle components that talk to the API server, because we don't want to DOS the API server. And for that reason, the binding might not succeed quickly, and so we needed a separate Go routine to keep trying until the binding actually succeeds. Now, we added an interesting extension point before that, which is what we call the permit plugin. And in permit, what we will allow plugins to do is to hold on to binding the pod until a specific condition is satisfied. And one use case that we had in mind is what we call gang scheduling. If you want to not actually start the pod until all the pods that belong to whatever, like for example, you can define them using a label selector, are schedulable, so they have been reserved and like some resource in a specific node, only at that point you want to basically say like release, okay, bind all those pods together and they will be scheduled together. So that's one interesting use case we had, and it's trying to make the scheduler sort of friendlier for batch workload. I don't think we are there yet, but we are trying to make it as such. So there are a number of benefits for the scheduling framework. Again, as I mentioned, it makes the scheduler easier to extend and isolate features. So before it was like a specific feature was spread across different files, and every time you want to add a new feature, like these ugly patches, it was harder for developers to actually fork the code and add new features. So we wanted to be more pluggable and basically isolate the features into a specific, all the features will be in a specific file that implements all the callbacks that gets executed in these extension points. And last but not least, previously we only had predicates and priorities, which is the one that I discussed earlier, scoring and filtering. Now we wanted to add more behavior and a more complex behavior, as I mentioned, the permit extension point and gang scheduling. So what is the status of scheduling framework? Like we're really happy to announce that the framework itself is fully implemented. It's in alpha right now. But then I think the next big, the other biggest thing that we did in 1.17, and I want to thank the SIG scheduling community for allowing us to do that, is we wrapped all existing predicates and priorities into plugins. So we had a chance to actually really make sure that the scheduling framework, its implementation actually works, covers at least the cases that we already have for the features that the scheduler implements. It required us, I think, over 100 PRs in the past few months. So it was a massive effort. During that, we don't want to break existing functionalities. We don't want to break the existing APIs that allowed users to define predicates and priorities through what we call policy files. And so we added this translation layer that translates legacy policy file definition of predicates and priorities into what we have now as plugins. So those plugins that wrap the predicates and priorities, they don't actually have substantial amount of code in them. The only thing they have is they're actually calling back into the older predicates priority functions. And so far we have two execution paths. One is active, one is not in the core scheduler. Hopefully now in milestone 2, 1.18, after we make sure that people, like in 1.17, we have no major regressions or bugs, we're going to completely deprecate all the predicates and priorities and move their code into native plugins, basically, to run as native plugins. And that will allow us to deprecate the old policy API. And hopefully, we will have the component config in GA by that time. And the replacement is going to be the component config plugin API for it. And milestone 3 in 1.19, we're going to actually deprecate the policy API completely and remove it and implement more features that we have in the scheduler as plugins, like preemption and the sorting logic and the binding logic, actually move them as plugins. And hopefully framework will be in GA. So the second development is performance improvements in 1.17. During this major refactoring, we identified a number of opportunities to improve the scheduler behavior. So we managed to improve the scheduler pod scheduling latency by 2x, but that's only for large clusters, like 5K clusters. And the other thing what we managed to do is also improve preferred pod affinity. That was an algorithmic improvement. We managed to change the complexity of the algorithm from N and P, where N is the number of nodes and P is the number of pods, to P, which is basically depends on how many pods you already have in the cluster, because affinity depends on that. You need to look at whatever pods they have running, and then based on that, you calculate where I'm going to place the pod. Another thing that we felt was a little bit lacking is improved observability. We had already a bunch of metrics that the scheduler produce, but we felt we can do better. So we tried to improve things across 3 different categories. The first one is latency. So until recently, we had scheduling latency of the attempt. So you don't know how long a pod was actually, it took us to schedule a pod, but the only metric we had was the scheduling attempt. As you know, a pod can be attempted multiple times, so we added a new metric to track how long it actually took from the time we picked up the pod from the Informer cache until the pod was bound to a node. And the other thing we added is latency breakdown of each scheduling step or plugin. So we have better tracing and ability to break down by, if you want to see, okay, why is my pod not getting scheduled, or why my scheduler is slow, you can now break down by plugins. Basically, you can see if pod affinity is the one that is, pod affinity plugin is the one that is, slowing things down, etc. The other thing is, categories is traffic. We added metrics to track number of incoming pods per second, so you can see how fast is the scheduler and draining that queue. And again, scheduling attempts per second. All those we felt are lacking in trying to understand whether the scheduler itself is misbehaving or is slow or for whatever reason. We just want more insights into the scheduler. Saturation, again, is related to how much resources the scheduler is consuming in terms of number of binding go routines that I talked about before, and the cache size. So the scheduler has its cache even on top of the Informer cache, because we want to annotate the nodes and the pods with extra information. So we have our own cache that we actually snapshot for each scheduling cycle, so that when we schedule a pod, we want to have a consistent state while executing all these extension points. So we were concerned about this overhead, so we're tracking the cache size, which is going to be proportional to how big is your cluster. That probably should help you also with, if you look at the history, how you provision the resources for the scheduler itself. Another thing that we implemented and we promised in previous KubeCons is pod topology spreading. I think it was on one of the keynotes. It was mentioned. Before that, we had pod anti-affinity, but pod anti-affinity wasn't really good enough, because it will only allow you to place one pod in different topology domains. With pod spreading now, you can define a skew. So you can say, okay, I want the pods that belong to a specific group to be placed in 2 different topologies with a skew of maybe at most 1. So you can always basically try to load balance properly across topology domains. I'm running a little bit quick because I want to leave time for questions. In 1.17, we graduated to GA a couple of interesting features. The first one is scheduling daemon set pods. Before that, daemon set pods were actually scheduled by the daemon set controller. So the daemon set controller was actually doing the binding, not the scheduler. So what we did in 1.17 is the daemon set controller just sets node affinity on the pod, and then leave it for the scheduler to actually schedule the pod. And that is better because it gives a more consistent view of the scheduler of what pods are running on which nodes and how much resources are being allocated. The other one is taint nodes by condition. There are some resources that don't get allocated, like disk pressure or PIDs, disk and PIDs. So, and sometimes the node gets into disk pressure or PID pressure, and even when you schedule the pod in the node, even if you have enough resources, it's not get scheduled because of that. So the node controller, what it does is it monitors the nodes, disk pressure, and for example, PID pressure, and taints those nodes with saying, for example, this node is unscheduled because of there's some resource pressure on it. Before that, we were looking at what we call node condition. Now we're looking at which is the more canonical way of how to place pods on segregating pods and nodes, is using taints and tolerations. There are a couple of planned features that are not completely scheduler related, but it's basically cross SIG. The first one is pod overhead. So with pod overhead, the problem is that when pods are started on a node, they have non-zero overhead. Think about the pose container that is associated with every pod. Also, the overhead of the components that are running on the node that runs the pod. For example, kubelet has some state associated with the pods that are running. So typically the way that we deal with this overhead is that we have a predefined amount of resources on the node for system components. But the problem is that we ignore per pod overhead like the pod controller, as I mentioned before. And now this problem becomes even more complex because we have sandbox pods. Like think about gvisor, Kata container. They have their own agents running beside the pod, and those consume resources, but those are not accounted for. And so here comes pod overhead. So with pod overhead, you can say at the runtime class level, this is how much resources that for this runtime class should be allocated per pod, and it gets propagated. And what we've done in 1.17 is that we implemented the scheduler part of that. So now the scheduler is aware of pod overhead, and when it schedules pods, it adds that overhead to the resources requested by the pod when it makes a decision where to place the node. So the scheduler part is implemented. The kubelet part is not, and that's why it's a planned feature, or it's under development. The other one that I really like, which is in-place update of pod resources. That's really interesting. Until recently, the resource request part of the pod spec was immutable. You can't change it. So basically, if you try to change it, the API server will reject the change. And so the only way to actually increase the resource of a pod is to actually delete the pod and create a new one, basically restarting the pod. Now, with features like vertical pod or the Scalar, we want to actually try to change the amount of pod resources associated with the pod while not starting the pod. And so now we have the KEP already merged. We agreed on the design. And hopefully in 1.18, we will start developing. There are two parts of it, the scheduler part and the kubelet part as well, similar to pod overhead. So there are many nuances here related to, OK, how do I do the memory, et cetera, scaling? Because, for example, Java-based applications, they take all the memory, so it will be hard to scale it down. But I mean, this is a long discussion. And that's the end of my talk. Questions? Yeah. Do you have a mic?
My use case calls for using multiple schedulers that have different algorithms for storing. One that uses traditional balance, and then one that uses density for spin packing. Mm-hmm. Will the new plugin-based approach allow you to choose either one of those within the same scheduler?
That's a very, yeah. Yeah, so right. So like right now, you could configure, like you can have two schedulers running, and as I mentioned, you can set the scheduler name, and you can configure them separately. What I would like to get to is I don't like the idea of having two schedulers. And what I would hope for is at the limit is to have what we call like scheduling profiles. So similar to runtime classes or storage classes. And so every group of pods, you can associate them with a specific scheduling behavior. And right now, it's something that we're discussing in SIG scheduling is how we define that API, that you express a scheduling behavior, so that you can run multiple workloads with different behavior in the same cluster. Because I mean, heterogeneity is useful, right? Like it allows you to bin pack better. It allows you to have better utilization. But in the short term, your only solution is to run multiple schedulers or multiple clusters. Weighted round robin?
Something like that. I mean, on a list of pods, if you want to do something like a weighted round robin based selection where each pod is assigned a weight, would the sort functionality help us there?
Are you talking about like how we gonna pick the nodes from the queue?
Not the nodes.
Sorry, pick the pods from the queue?
Pod to run next. Yeah.
Yeah, so that's exactly like so we have this sort plugin here. This is going to change the way that you order the pods in the queue. So the problem is that this is fixed. Right? You can't have multiple sorting criteria. So you can have only one.
Okay. But which sorting algorithm you use is up to the plugin writer to choose? Would that be the case?
Yeah, exactly. So you would need to write your own plugin and compile it in.
Okay. One follow-up on this. Will we be given a list of pods and we pick a pod, or will we be given a list of pods which we sort and then return the list back to the schedule?
I think you would right now so you would implement the list function. That's what you do. So it's much simpler than that. Yeah. Uh-huh.
Could you give that graph? How do you think that will work?
So at the high level, the permit allows you to wait on a pod for a specific time, like we have a timer. And if that timer expires, the pod basically gets rejected. Now, the idea is that, like for example, you have pod 1, 2, and 3. So pod 1 when your plugin will return, for example, wait for 5 minutes. Pod 2 will come, and then you say wait for 5 minutes. Then pod 3 will come, and then what you can do, like what the framework will allow you to do is you can check which pods are waiting right now. And so you're going to have to define your own criteria of when to say, OK, those pods that are waiting, accept them, and accept myself and move on. So the state is there. The pods that are currently waiting, you have access to them. And so it depends on the plugin implementation of when to decide how to accept all the pods that are currently in waiting state. Yeah. 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 Basically getting more insight into the scheduling behavior. So basically what we wanted to do is to get more metrics into what the scheduler is doing. For example, how many pods is it scheduling per second? What is the length of the scheduling queue? How long it takes to schedule a pod. So those metrics in collection, we call them like it's under observability. We wanted more insight into what the scheduler is doing. Sorry. Go ahead.
Hi, could you elaborate a little bit how the scheduler interact with the cloud autoscaler and pod autoscaler, and which level they collaborate with each other?
Right. I think we have Vivek here, right? You want to talk about it?
I didn't quite get the question.
Yeah, so I was wondering how the scheduler.
Actually, should we do this after the questions because we don't want to.
Do it on the microphone so we can all hear.
Yeah.
Okay, so the question is how the scheduler interact with cloud autoscaler and also other scheduler autoscaler.
Thank you. So the question was, how does a cluster autoscaler interact with the scheduler? Basically, we have the scheduler code inside cluster autoscaler. So the cluster autoscaler needs to understand how many nodes to create for a certain amount of pending pods to be scheduled. And for that, we need to understand how many pods we require. So we basically have to run some of the filters to figure out if these many nodes are enough to run these many pods. So there is basically a one-to-one mapping between the amount of cluster autoscaler version and the cluster and the scheduler version. So if you're running, let's say Kubernetes 116, you would require a cluster autoscaler the exact same version because the cluster autoscaler would use the exact scheduler code for that particular version. Yes, 2 controllers. Thanks.
Thank you.
How does that work with the scheduler framework? Do you have to configure the autos? How does that work with the scheduler framework? Do you have to configure the autoscaler with the same plugins and stuff?
Exactly, yeah.
Yeah, okay.
Yeah. My hope is that if we get to the point where we define this API that you can define those different scheduling behaviors, is the cluster autoscaler as well looks at that API. For example, imagine that it is, again, CRD, which is like now it's the hot thing, right? Like you define it as a CRD, you have that state. This state basically defines what are the plugins that I want to run, which weights. And then the cluster autoscaler basically has the pod, knows which exact configuration it has to configure when it's trying to evaluate that pod for autoscaling.
Hey, good talk. Lot of improvements. So one question about the gang scheduling, which
Sorry,
you just.
I can't see where you. Oh, sorry.
One question about the gang scheduling, which you just mentioned. How can you make it consistent without the quota management on top of it? So I'll take an example. You have like 3 pods. You are waiting for 2 pods, and the third pod is not arrived yet, and you're waiting for it. But if you are not doing a quota management at the admission control level, what is going to happen is you don't have enough resources, and the more other pods going to come and take the resources, and the first 2 pods will going to time out. Then it will go into again into the scheduling cycles.
Right.
And then this churn will keep on happening.
Yeah.
So you need to have quota management on top of it before we do that.
I have to admit, like we did not really make any progress on that yet. So those are very legitimate concerns. And I think it's one of the planned features for us is to start thinking more and more about batch workloads and how we integrate them with the current scheduler.
We have Peloton, which we can talk about it.
Yeah.
Which does that.
Yeah.
So regarding the framework structure, do you plan to add any observability plugin, something that produces metrics at some points of the pipeline that tells you about the quality of the scheduling you're performing? Like if you want, imagine you implement one of the modules apps, like, I don't know, like the sorting, because you want to enforce you want certain jobs to be scheduled first, but you want to measure if those jobs actually got sorted first. Would it make sense to have a plugin at the end at the bind stage that it will produce metrics that you can program on your own?
Yeah, I mean, like some of these actually extension points are, like we call them like informational. And our vision is that some of them are going to be going to either emit logs or emit metrics based on previous, like the behavior in the previous extension points. Did I get your question?
Yeah, but if I want in real time, like for example, what we do, for example, is we produce metrics saying, okay, we place one job for this user and that goes to Prometheus, and in real time we can see what is the rate of jobs per user that we are okay. placing, right? And if I would have this framework, I wouldn't like to have to make a wrapper for the bin thing to add the metric that that propagates the metric somewhere else. It would be great if I could monitor all the jobs I get then without modifying anything, just by making a plugin that observes whatever goes into bin, and then I extract my custom metrics that have to do with my way of doing scheduling, and I just publish them. But I don't want to taint anything else in the structure. That's what I mean.
Yeah. I don't have any thoughts on that. I don't know if it would work. The problem is that metrics in Kubernetes in general is like, I think it's strict of some sort. Like you have to predefine them, and yeah.
Do you have any updates on the descheduler, whether that's going to be rolled into the scheduler at all, or is that sort of just a side project still?
It is still a side project, but it's, I don't know if Ravi is here. Can you talk about it?
Yeah, a little bit. So the descheduler is just recently updated to 1.16. So it has been kind of dead for a little while. Oh, Ravi is here. So yeah, it's, I don't know if there's any plans to move that soon, but it is a plan to move it to GA eventually, and we're working on getting it up to pace and, you know, at a spot where everyone can use it. In a nutshell.
Yeah, just to add to what Mike told, so we haven't thought about it, but if you think that there are some use cases where descheduler would actually benefit if it's part of core scheduler, we can make it as part of a plugin at some level. So it depends on the use cases. Like if you have something, please let us know. We'd be more than happy to look at it.
What's a descheduler?
Did you attend the intro yesterday? I'm sorry, just kidding. Descheduler at high level is an evictor whenever the scheduling decisions are not met anymore. For example, once the pod comes into running state, the default scheduler would not even care about the pods anymore. So at that stage, if descheduler sees that there are some pods that are in running state and they are not conforming to the scheduling constraints anymore, it would evict those type of pods. Again, while evicting, we have some constraints in place, like we will not evict every pod, but this is what is the job of descheduler. There are some other use cases for it too, like for example, if you want the cluster to be defragmented, say if there is a lot of fragmentation, we can use descheduler as a high-level defragmentator too. Does that answer your question?
So I have a question for the sorting function, because that assumes you already have all the pods, but imagine like in a batch case, you have like a stream of pods. Can we make that interface like more like kind of like?
So what we have is actually a priority queue, and what you're going to give is the compare function. So that's what it is.
Yeah, but the question is like many times some functions could be more complicated than just compare function.
Yeah.
Like for example, like a young queue, right? So basically you have to based on the current entitlement of that queue to decide who should move to next.
Right. If you have like a specific like really, you know, like use case for it, it would be more than happy. Like if you can file an issue, like the framework right now is still in alpha. We are interested to improve the extension points that we have to cover more use cases.
Yeah, that would be awesome.
Yeah.
I have one more question is, you said we're going to start to support in-place resource update,
yeah,
which is awesome.
Yeah.
But now my question is, we also have lots of use case, which we kind of need in-place container update. For example, like, you know, for some machine learning use case inference, we have some inference container, and then we also want to treat each model as a container, so they're all in the same pod. But we want to upgrade those model containers without bringing down the inference container.
I think it's per container. Like the resources are actually defined per container. So what I just described, like the name is misleading. It's actually per container. Like when you modify the resources, you are modifying.
Okay, you mean like modify resources per container? But my question is like, if we want to kind of replace the image of the container, is that going to be supported?
Oh, okay, yeah.
Without bringing down the pod.
Right,
like,
right.
Of course, container will be restarted, but like the other, let's say you have one pod with two containers, if I only replace the image of one container, then I don't want to bring down tear down the.
Right. So you just want to restart one container.
Yes.
Yeah. Yeah, that's a good SIG node question.
Well,
Yeah. No, but that's a very interesting, valid use case.
So it sounds like for the scheduling framework, your plugins have to be compiled for environments like a GKE. It's not really available, right? Is there demand for making like webhook plugins? It seemed like I had heard about performance concerns, but it seems similar to like a mutating webhook admission controller would have the same sort of performance impacts.
Not really. Like that's the problem, as you mentioned. Like it's performance. Once you start making these calls to various,
Yeah. My point is that it seems like the amount of performance impact would be similar, but I don't know. Maybe it's not.
So at which stage of scheduling are you talking about? Like, are you talking at the scheduling stage or the pod admission stage? If the admission, if the webhook needs to be called during the scheduler or after, or at some stage of scheduler, it is already available. We have a HTTP extender. Like at predicate stage or priority stage or bind stage, you can make an HTTP call if that's what you are asking for. And that still exists, and that will continue to exist as well.
Yeah. It doesn't exist in GKE, but
yeah, in GKE, but it exists in open source.
Thank you.